Alright, it's time for our next unit. So the title of this unit is Solutions and Reactions, and those two go hand in hand because a lot of reactions take place in solutions. There's very few solids that will react. So, I mean, if you have a pile of one solid and a pile of another solid, even if the two compounds would react, just pushing those two solids together isn't necessarily going to trigger a reaction because you don't get kind of the mixing that you do with a solution. However, if you take both of them and dissolve them in beakers of water and then mix the two solutions together, you would get a reaction. And so that's why solutions and reactions go hand in hand. So just to start off, some definitions of a solution. So a homogeneous mixture is a solution. You can't really see the difference between the different parts. It's composed of a solvent and a solute. So the solvent is what does the dissolving. The solute is what is dissolved. Great way to think about the difference is the solvent is the one that you have more of. The solute is the one that you have less of. And typically the solvent is the liquid, like water, and solute is the solid, like salt. But it doesn't always work like that. Sometimes you're mixing two liquids together, like water and alcohol, in which case whichever liquid you have more of would be the solvent, and the one that you have less of would be the solute. So if you have like 100 milliliters of alcohol and 10 milliliters of water, and you mix those together, alcohol would be your solvent, water would be your solute. And an aqueous solution then is one where water is the solvent. So anytime that you have something that has more water than something else, it's an aqueous solution. One of the properties of ionic compounds is they are electrolytic when put into a solution. So what this means is if we take an ionic compound and we dissolve it in water, and so let's say sodium chloride, that's the example they give, that's an ionic compound. When you put that in water, it doesn't stay sodium chloride, it breaks apart into sodium ions and chloride ions. And obviously there would be a lot more than that, but they're just enlarged to show texture. So you'd have those sodium cations, those chloride anions floating around in solution, and if we were to take a conductivity tester, we've used them in class before, just has two prongs that go into the solution, and then some kind of power source, like a battery. Okay, if you normally just set this out in the air, no electricity is going to get across because you need those 2 points right there to be connected. However, when you put it in an electrolytic solution, what can happen is the electrons that flow with electricity can actually bounce across those ions and go from one side to the other. It's called a salt bridge. And when that happens, you close this gap up, and that means that your light bulb can shine. So it's conducting electricity. And only electrolytes can do this because electrolytes produce those ions, which means electricity can conduct between them, making that salt bridge, therefore turning on your light bulb. And also, the more ions that are in solution, the better it will be able to conduct electricity. So if you were to increase the concentration of sodium chloride in here, the light bulb would burn even brighter. Okay, so but a little bit of salt, maybe not as bright. Alright, here's a general equation. This is how we show something dissolving in water. So this is important to remember. Even though water is involved, water is just a spectator. It's what causes something to dissolve. It's not actually reacting itself or changing itself. So when we talk about sodium chloride, table salt dissolving in water, we would write it just like this. So we have solid sodium chloride ionizing into Na plus and Cl minus. We can do this with any ionic compound that's going to ionize. So something like MgSO4 is going to ionize, and that would be a solid, into Mg2+, which is aqueous, and SO4, 2-, also aqueous. And of course, balancing matters, so if we have something like MgCl2, magnesium chloride, which is a solid, and we dissolve that in water, it's going to ionize into Mg2+, which is aqueous, and 2 Cl- is also aqueous. And so that just shows that since we have two chlorides, we have two chlorides right there. So let's take a look at this dissolving process on the molecular scale. So what happens when an ionic compound dissolves is it goes through what's called solvation. We've talked about the polarity of water already and how the difference in electronegativities between oxygen and hydrogen causes the oxygen to have a negative dipole and the hydrogens to have a positive dipole. As a result, then, we've also, in the ionic compound, got positive cations and negative anions. So the negative charges on the oxygens are going to surround those cations. because they're going to be attracted to the positive right there. And this is a two-dimensional picture, but imagine this surrounding it three-dimensionally, so on all sides surrounding it. And chloride, on the other hand, is going to be attracted to the delta positives on the hydrogen atoms. Once again, imagine those surrounding it three-dimensionally. As a result, then, water separates the Na from the Cl. Before it's put in water, it's NaCl. It's sodium bonded to chlorine. But once you put it in water, the water actually rips them apart. Such a little home wrecker. And the salt will stay dissolved because the water keeps it separated. Now, when we hit saturation, like if you keep pouring salt into the water, eventually the salt's going to stop dissolving. And that's because all the water molecules are already tied up, holding other guys apart. And so you end up having enough Na pluses and enough Cl minuses that they can no longer keep them separated. And so they start coming back together, reforming that salt at the bottom. So if we take two different ions that we have in a solution, so these are both dissolved in water, and we put a positive plate and a negative plate inside there. That's just an electrical charge. What's going to happen then is this negative is going to attract both of those cations. If it was anions, they would be attracted to the positive side, but we're dealing with positives here. So these vectors, or these velocity arrows, are drawn to scale. What this is showing is that the cesium, which is larger than lithium, is going to travel faster towards this negative plate than that guy is. And it's because of Coulomb's law. So Coulomb's law says that the radius makes a difference in the electrical charge, electrical pull felt by the molecules. And since the positively charged nucleus is a lot farther from the water molecules in cesium, it means the water molecules aren't going to attach as strongly to the outside, so there won't be as many water molecules. That means it can cruise through the water pretty quickly. The lithium, on the other hand, has a shorter distance from its positively charged nucleus to the outside. That means more water molecules are going to be attracted to the outside. And as a result, it's going to kind of slow it down as it moves through. Think of this like going through a crowd. If you've got someone who smells really bad moving through a crowd, people are going to get out of the way, and it's going to be able to move through pretty quickly. If you have someone really cool and popular trying to go through a crowd, like imagine this is Justin Bieber going through a crowd of girls, they're going to surround him on all sides and slow him down as he moves through. Okay, so that's all ionic compounds. Now let's talk about molecular compounds. So molecular compounds are things that are bonded covalently to each other. And there's really three different types. There is non-electrolytes, there's weak electrolytes, and then there's strong electrolytes. So a non-electrolyte would be something that does not conduct electricity, and it doesn't conduct electricity because it does not dissociate. It does not mean dissolve, it means it does not dissociate. And so let's take a look at what those terms mean. So dissolve and dissociate do not mean the same thing. So for example, sugar, C6H12O6. When we put that into water, it dissolves. Okay, we've seen sugar dissolve in water before. However, it does not ionize, so it doesn't break apart into ions. It stays C6H12O6, except now it is aqueous. All right, so that is dissolving right there. It's not dissociating because it's not breaking apart into ions. The antithesis of this would be something like sodium chloride again. So sodium chloride starts as a solid. When we put it in water, it ionizes or dissociates into Na plus and Cl minus, both of which are aqueous. So then let's get the terms straight. Sugar dissolves, but it does not dissociate. Sodium chloride dissociates, but we would also say it dissolves in water because it disappears. Dissolving just means we can no longer see it. Disappears into the water. And sugar would not conduct electricity because there is no ions for the electrons to jump across. However, something like sodium chloride does because the electrons can jump across those charged ions. And then a weak electrolyte, something like acetic acid that they give in the example. Acetic acid dissociates, which means that it will ionize slightly, but it won't completely ionize, which is different than everything else. So like sodium chloride, when we put sodium chloride in water, it all breaks apart to Na plus and Cl minus. When you put something like acetic acid into water, it breaks apart into H plus, CH3COO minus, but some of it stays in its original form, aqueous. It's not solid, okay, so it's not like it stays as a solid, then partially dissolves. It only partially dissociates. So inside of the solution, inside of the water, you would have all three of those in there. And then the last one is strong electrolytes. So these would be things like strong acids. They completely dissociate in water, which means just like sodium chloride, just like ionic compounds, they break apart into all of their ions. So H pluses, Cl minuses. All right, and here's that term again, like dissolves like. So what it says then is that nonpolar molecules dissolve in nonpolar solvents. Polar molecules dissolve in polar solvents. So not just ionic compounds dissolve in water. Any polar compound will dissolve in water. For example, methanol, which is this big guy right here, will also dissolve in water because it has your dipole negatives and your dipole positives. So they can be surrounded by the water molecules just like sodium chloride can. And things like styrofoam or paint or permanent markers that we think of that don't dissolve, it's not that they don't dissolve, they just don't dissolve in water. They dissolve in non-polar solvents. So there is things that will dissolve paint and styrofoam and Sharpies. It just can't be done with water.